Hello, this is Dr. Joe Trout from the physics program at Stockton University, and this is the continuation of Chapter 9, speaking on the ARIMA models. And we'll continue on talking about the moving average models and the non-seasonal ARIMA models, and the estimation and order selection, and ARIMA modeling and forecasting, and then the seasonal ARIMA models, and the difference between ARIMA and ETS. First, let's talk about the moving average models. So in this case, the moving average models are part of the ARIMA family, and they're used to model time series with autocorrelated noise. So forecasts are going to be based on past error terms, not on past observations. So if you think about autocorrelation, right, it's once again, it's a mathematical representation of the degree of similarity between a given time series and a lagged version with successive intervals. And it's conceptually similar to the correlation between two time series, but the autocorrelation uses the same time series and the original form and once lagged version or lagged one or more time periods. So if you have an autocorrelation of +1, then we see that it pretty much follows, the two time series follow one another. And if we have an autocorrelation of -1, then when one goes up, the other one goes down. So if we look at the moving average model definition, we have our value y of t is equal to some constant plus some residual or error term, and this error term should be white noise and plus theta 1 times the error from 1 time step back, and then theta 2 from 2 time steps back up to q. And theta 1 is the parameters that have to be estimated. So the characteristics of the moving average models is that they have a short memory, so they're limited to the past q errors, not to the entire time series. And they're always stationary, and they're not invertible unless there's certain constraints placed on theta. And we'll talk more about that later. And it's useful for capturing shocks or irregular patterns. So if we think about invertible versus non-invertible in a moving average model, the moving average model for a order of q is that y, once again, is equal to the some constant times the error at time t plus the error at t-1 and t-2, and where these errors are considered to be white noise. So at the invertible moving average model, the moving average model is called invertible if it can be rewritten as an infinite order of autoregressive model with stable coefficients. That is, you can express the error at time t in terms of the past values of y of t. And this makes the model practically useful for estimating and forecasting. And an invertible ensures the uniqueness of the moving average representation. And there is one set of moving average parameters that represent the data. Mathematically, the roots of the MA polynomial, where we have 1 plus theta 1 times z plus theta 2 times z squared up to theta q times z to the q t raised to the power of q, must lie inside a unit circle. So the root, the absolute value of the root has to be greater than 1. For non-invertible, right, it cannot be written as a stable autoregressive process, and the same autoregressive function, ACF function, can be generated by both invertible and non-invertible moving average models, and this leads to a non-uniqueness of the parameter estimates. And it makes the model unstable or poorly estimated. So in practice, most statistical software such as Fable and Forecast and stat models automatically constrain MA models to be invertible during the estimation. So in summary, if with an invertible model versus a non-invertible model, if we can be written as an autoregressive function, yes to the invertible and no to the non-invertible, and unique parameters, yes to the invertible, and numeric stability, the invertible is stable, and in common in practice, right, the yes, and it's rarely used, the non-invertible is rarely used. So the invertibility is required to ensure that the parameter estimates are meaningful and that the forecast is reliable. So when we look at what stable AR processes are, so if we look at the autoregressive process of order P, it looks like this function here, right, where we have our value at y of t is equal to some constant times the previous value for y plus a constant times the 2 time steps back and so forth. And finally, added some white noise. And the stability means that the time series doesn't blow up over time. It remains bound and does not exhibit explosive behavior. Shocks have diminishing, and the shocks would actually have diminishing influence over time. And if you hit the series with a shock today, the shocks affect decays gradually instead of causing the values to grow indefinitely. And the process is stationary, of course, if you remember, if we have a constant mean and a constant variance and a constant covariance over time. And you can write the AR process of the polynomial as we said, 1 minus theta 1 times z minus theta 2 times z squared minus up to theta p, z to the p, right? And we set them equal to 0, find the roots, and as we said, the absolute value of the root should be greater than 1. If it's not stable, the AR process is non-stationary or explosive, and shocks grow or persist forever. And the series does not have a well-defined mean or variance. So if we just look at an AR1 process, we have the value y of t is equal to theta 1 times the previous value for y plus some residual or error term. If it's stable, the absolute value of theta 1 will be less than 1. And if it's equal to 1, then we have something like a random walk that we've spoken about in previous chapters. Or if it's greater than 1, then it's going to be explosive. So for a stable AR process versus an unstable AR process, number 1, is it stationary? Yes for the stable. Bounded? Yes for the stable. And the shocks fade out? Yes for the stable. So here's 2 examples. If you look at a shock that occurred at time t equals 10, and then we have a process where theta is equal to 0.6. Sorry, I repeated this value here. That's okay. And time t equals 1. And what we see is that after the shock, this orange model, the unstable one, starts to grow. And theta is equal to about 1.05. It's greater than 1. And if we look at the yellow line, it has the shock and then it returns to near the original average, and we have a stable version. So here we see another example where we would have a shock and it would slowly return to its stationary values. So here's an example. We have MA1, where we have y of t is equal to a constant times some term at t plus theta 1 times the previous value for the term. And it's in a simpler form, is easier to interpret, and each value depends on one lagged error. And if we look for an MA2 model, we'll see the two values here. So if we look for moving average models, it's possible to write any stationary autoregressive model with a moving average model. And for example, using a repeated substitution, we can demonstrate that this for an AR1 model, right? So for example, if we have y of t is equal to theta 1 plus the previous value for y plus some error term, and but to get theta 1, to get the previous value for y, we can estimate it from 2 time steps ago, and we'd end up with theta 1 squared times the previous value for 2 time steps back, plus theta 1 times the previous error for the time step, plus some noise. So if we want to simulate a moving average model and an invertible version, and what we can do is load forecast and time series and simulate the invertible M1 process. We'll set theta equal to 0.5, and then we'll set a seed for it, and then make an array of we'll call it MA invertible, and we'll set up a set of values. Then we can fit the moving average model, and we'll use the ARIMA model where we have 0, 0, 1. And then we'll check the estimated coefficient and invertibility, and we'll go ahead and print the values. We'll also simulate a non-invertible moving average model, and we'll set theta equal to 1.5, right, which is greater than 1, and we'll fit the model and compare the two. So here we have an invertible moving average model, right, with some data, and this is the non-invertible moving average model, the data that's shown, and this is the raw data versus time. If we look at the ACF, right, we can see that they're reasonably similar, and what we see is that with the ARIMA 001 with a non-zero mean, then we have the coefficients that we can set up. And if we look at sigma, the likelihood, we come up to about 0.92 and about -274. Sorry, this log is hidden, but we can see how this affects, the non-invertibility affects the moving average model. So if we look at the ACF and the PACF behavior, the ACF cuts off after a lag Q, and the PACF tails off gradually. And this is useful for identifying the moving average order that we can use, so it helps us see it visually. So for forecasting with moving average models, the forecasts use the known past errors in the sample, and beyond the training period, the error terms are set to 0, and it forecasts quickly to revert to the mean. The limitations and use cases, it's not suitable for data with trends or seasonality. In that case, we definitely need the ARIMA model, and it's best for short-term shocks and residual modeling. And often it's combined with the AR parts in the ARIMA model, or the ARMA model, and we can use it. So in summary, the moving average model uses past errors for prediction, and it's always stationary, but it's harder to estimate. And it's key in the ARIMA framework, and ACF will help identify the moving average order. So if we look at non-seasonal ARIMA models, what we're going to have is that our ARIMA model will be will be set by looking at the order of the autoaggressive part and the degree of first differencing involved and the order of the moving average part. So in the ARIMA non-seasonal, we're going to combine differencing with autoregressive and a moving average model. And the acronym, of course, is for autoregressive integrated moving average. And in this context, the integration is the reverse of differencing, which may sound familiar if you've had calculus at some time in your career. There's a couple of special cases of the ARIMA model. So white noise can be modeled with ARIMA 000 with no constant. And the random walk that we talked about in the previous chapter or the previous lecture, we have the ARIMA is equal to 0, 1, 0 with no constant. And if we have the random walk with a drift, it's 0, 1, 0 with a constant. And if we're looking for just an autoaggressive, then we can use just P 0, 0. And for a moving average, it's 0, 0, Q. So once again, P is the order of the autoaggressive part, D is the degree of differencing, and Q is equal to the order of the moving average part. So we're going to take a moving average part and an autoaggressive part and put them together. So if you remember when we talked about backshift notation, we can write it as the autoaggressive part, where we have 1 minus theta 1 times B up to minus theta P, phi P times B to the P. And then difference it, we have 1 minus B raised to the D times the value Y of T, and this will be equal to the moving average part, where we have a constant plus 1 plus theta 1 B plus up to theta Q B to the Q with our noise term. So for selecting the appropriate values for P, D, and Q can be difficult, and most of the packages that have the ARIMA model will do it for you automatically. So for example, here's a ARIMA function for the Fable package, and it will do it for you, as we said, automatically. So we can set, for example, the global economy, and we'll use the database that's included in the package, and we'll set the code equal to USA, and we'll auto plot the exports and show the labels for the exports, and then we'll fit the ARIMA model to the exports and look at how it works. So in this case, we'll just tell the ARIMA model, we won't give it any values, we'll let it find the values for ourselves. So in this case, we'll get an output, and we see that the ARIMA model found the best model was 0, 1, 1, and tell you what the coefficients are, and tell you what the AIC and the AIC corrected and the BIC are. So in this case, we'll take it and go ahead and plot some data and also predict what it will be in the future and show the two levels, the 80 and 95%. Here shows the ARIMA 110 model, and once again, another example of how we would predict the future. And have our values for AIC and AICC and the BIC. And in this case, we're using the ARIMA 201. So don't forget, um, the P is for the order of the autoaggression, and D is for the degree of first differencing, and Q is for the moving average part. So in this case, we end up with a ARIMA 201 with a mean. So for the ARIMA model, we have the order of aggressive, the first order of aggressive, autoaggressive part, and the degree of first differencing, and the Q is equal to the moving average part. And some caution should be used when using these automated functions. So the constant C has an important effect on the long-term effect, the long-term forecast obtains from these models. So if C equals 0 and D equals 0, the long-term forecast will eventually go to 0. And if C equals 0 and D equals 1, the long-term forecast will go to some non-zero constant. If C equals 0 and D is equal to 2, then the long-term forecast will follow a straight line. And if C does not equal 0 and D equals 0, then the long-term forecast will go to the mean of the data. And if C does not equal 0 and D equals 1, then the long-term forecast once again will follow a straight line. And if C is equal to 0 and D equal to 2, the long-term forecast will follow a quadratic trend. So the moving building blocks of ARIMA are the autoaggressive terms, the integrated or differencing, and the moving average term. So first we need stationarity, and this is a key concept, and it's for the ARIMA model. So stationary series have a constant mean and variance over time, and they're required for the ARIMA model to be valid. So what are we going to do? We're going to take the autoaggressive part of the model, which should look familiar, and take the moving average part of the model, or the moving average model, and then we're going to combine the two. And first we have the ARMA model, and it combines the AR and the MA components, and it assumes that the data is stationary. Differencing for stationarity, so we could take the first difference and we'll come up with y prime of t is equal to y of t minus the previous value for y. And we can use higher order differencing if needed. So for the ARIMA, we have P is for the autoaggressive part, D is for the differencing part or differencing order, and Q is for the moving average order. We'll use ACF or PACF plots and stationarity checks to identify the appropriate values. So ACF helps detect for the moving average part, and PACF helps detect for the AR part. So for estimating these parameters, the parameters estimated using the maximum likelihood or conditional sum of the squares, so ML or CSS. So if we want to estimate and order selection, right, what we'll do is we'll take model estimations and time series, and the objective, of course, is to fit the model parameters to the data. And the common modes we'll use are the autoaggressive, the moving average, and ARIMA models. And the techniques, we can use the least squares and the maximum likelihood. So with the least squares estimation, it minimizes the sum of the square residuals. that we've talked about in several chapters. And it's common for linear models, for example, the autoregressive. And it's simple, fast, and interpretable. The maximum likelihood estimation finds the parameter values that maximize the likelihood. And they're more flexible and can handle complex models better. And it's preferred for the ARIMA models and other models. So when we're assessing the model fit, we can use residual diagnostics. So we'll use residual plots and ACFs of residual plots and the Lejeune box test, and the residuals should resemble white noise. So we also use information criteria, and we used to compare models with different orders, and we'll balance fit and complexity. So don't forget, we want the simplest model that accurately predicts the future, right? So we try to limit complexity as much as possible. And the common criteria is the AIC and the Bayesian information criterion, the BIC, that we'll use to do this. So for if you remember the AIC, it's equal to minus 2 times the log of k plus 2k, where k is the number of parameters. So this is going to penalize you for having more and more parameters. And also L is for the likelihood. And it's a lower AIC predicts a better model or indicates a better model. For the BIC, it's equal to minus 2 times the log of L plus k times the log of n. And this is penalizing complexity more than the AIC. And it's often preferred when the sample size is large. So we're going to fit several models with different PDQs. And so it's different order of aggressive part and the degree of forced differencing and the order of the moving average part. And then choose the model with the lowest criterion and also check residual diagnostics. So when using Fable, the Fable package, it estimates the ARIMA model and it uses the maximum likelihood estimation. And this technique finds the value for the parameter, which maximizes the probability of obtaining the data that we observed. So for the ARIMA models, the MLE is similar to the least squares estimate that would be obtained by minimizing the sum of the errors squared, or the sum of the residuals squared. So for the information criteria, we'll use the AIC. And in this case, it's equal to minus 2 times the log of L plus 2 times P plus Q plus K plus 1. And where L is the likelihood of the data, and K is equal to 1 if C does not equal 0, and K is equal to 0 if C is equal to 0. And note that the last terms in the parentheses are the number as the number of parameters in the modeling. So for the ARIMA model, we can also use an auto-corrected or a corrected AIC, right? And the formula is given there. So it's the actual AIC plus 2 times P times Q times K plus 1, and over T minus P, where T is a period, and P minus Q minus K minus 2. And finally, for the Bayesian information criterion, or the BIC. And once again, most good modeling packages will figure this out for you. So in summary, we look for an estimation of fits the model parameters, and the AIC and BIC will help select the optimal order, and we'll combine criteria with residual checks, And of course, the goal is an accurate model. So let's look at modeling in Fable, right? So we're going to use the KPSS test, the test for stationarity of the time series. And this test checks for the null hypothesis that a time series is stationary around a deterministic trend. So we start with the null hypothesis that the series is stationary. So it's either level or trend. And the alternate hypothesis is that the series is not stationary. And Fable is going to use via feast and find what the values are. So the output um, is going to be if p is less than 0.05, we'll reject the null hypothesis, and the series is non-stationary. And if p is greater or equal to 0.5, it fails to reject the null hypothesis, and the series is stationary. So if we look for the algorithm that's used, the number of differences is between 0 and 2 is determined using repeated KPSS tests. And then the values of P and Q are chosen to minimize the AIC after the differencing the data D times. And rather than considering every possible combination of P and Q, the algorithm uses a stepwise approach to do this. So the four initial models are fitted 0D, where D is the differencing between 0 and 2, 0, and then ARIMA 2D2, and then 1D0, and then 0D1, and the constants is included unless D is equal to 2. And then if D is less than or equal to 1, then an additional model is also fitted, which is 0D0 with a constant. And the best model with the smallest AICC is fitted in step A is set to the current model. And then variations on the current model are considered. So we'll go ahead and vary P and Q and from the current model by plus or minus 1. Then we'll include or exclude C from the current model, and the best model considered so far, either the current model or the one of the variations become the new current model. And then we can keep repeating this until no lower AIC is found. So what we're saying is we'll just keep trying a bunch of PDQs and find out which one is best. Graphically, it looks like this, and we'll go through this graph in just a second. So first, step 1 are shown in these orange dots, and we'll start with P equals 0 and Q equals 0, and then P equals 1 and Q equals 0, and Q equals 1 and P equals 0, and so forth and so on. And then we go to Q equals 2 and P equals 2. So let's look at how this works, right? The grid AR is increasing, P increases vertically, and the moving average Q increases horizontally. And it starts at the ARMA model 0, 0 in the top left-hand corner. So these are the orange cells, and we set the initial set of models considered. And the AIC is used to evaluate the model quality. So let's say ARMA 2.2 has the lowest corrected AIC in the initial set, and it becomes the current model. So that's where the black circle is. From there, we use a stepwise selection. So the ARIMA evaluates neighboring models shown by the blue arrows. So it'll try 1-1 and 2-1 and 3-1 and so forth, and uses these models. Let's say that now we find out that this was the best one so far. And then we try to move out to these green spaces and see if they do better. There's no reason to check these spaces or these values because we already checked them. So we're searching through for the best value. And let's say, for instance, we find that when we try these green values, we find that Q equals 2 and P equals 4 is the best one. Then we'll try these values here and see which one is the best one. So as we move through, for instance, here, the green model 4-2 becomes the new current best model, and we'll check the other values in the pink. So we could do the full neighborhood search in which you set greedy equal to false, and it avoids approximations. And we can, if you want to avoid approximations, we can set approximations equal to false. And to search for a larger model space, we can set stepwise equal to false. And the default setting may not find the global AICC minimum. So we can either do things really fast and try to find out what the best model is, or we can search for through everything. So once again, the modeling procedure to fit the RRM set of non-seasonal values in a time series. First, we'll plot the data and identify any unusual behavior. And then if necessary, we'll transform the data to stabilize the variance. And if the data are not stationary, we'll take the first difference of the data until the data are stationary. And then we'll examine the ACF and the PACF, and we'll use and look as an ARIMA PD0 or an ARIMA 0 DQ model appropriate. And then we'll try to choose models and use the corrected AIC to search for a better model, and then check for the residuals from the chosen models by plotting the ACF of the residuals and doing some tests to see if they look like white noise. If not, we'll go back and modify the model again. And then once the residuals look like white noise, we'll calculate the forecast. So we plot the data, identify unusual observations. If necessary, we'll use the Box-Cox transformation to stabilize the variance. Then we'll use an automated algorithm. So we'll use ARIMA to automatically find the best ARIMA model for your time series, or we'll select the model yourself, and if necessary, difference the data until it appears stationary. If not, use the unit root test if you're not sure, and then plot the ACF and the PACF of the difference data and try to determine the possible candidate models, and try to choose your chosen models to use the AIC to search for a better model. And then finally check the residuals of your model by plotting the ACF of the residuals and doing a test to see if it looks like white noise. So do the residuals look like white noise? Yes, calculate the forecast. No, go back and keep trying. And by the way, if you use the automated version and it does not look like the residuals don't look like white noise, then you have to do it by hand. So if we look for Portman to a test to check whether residual resemble white noise, and it tests the autocorrelation across multiple lags simultaneously. And common tests are the Box-Pierce test and the Lejeune-Box test. And the null hypothesis is that the residuals are uncorrelated white noise. So when we use the Lejeune box test, we'll look for the statistics, and N is the sample size, and RK is the autocorrelation at lag K, and H is the number of lags. And if the p-value is less than 0.05, we reject the hypothesis, the null hypothesis, and the residual show autocorrelation. So good ARIMA models should have residuals passing this test. So here, if we use the global economy database and we filter for, say, Ireland, right, and look for Ireland exports and the percent of the GDP, we see a value that looks like this. And we'll go ahead and filter it. So we'll look at the difference and plot the type and plot it. So the difference of the exports and show the ACF and the PACF. And the blue lines show the limits that we should use. So we see that 1 is pretty high here, and also at this would be 7 is a little bit above the value, and for the PAC we're up at 1. So if we look at the different series appear to fluctuate around a constant mean, and suggesting that the first difference might have obtained stationarity. And if we look at the ACF, it cuts off after lag 1, right? And there's some smaller lags, and later there's some larger lags, but it pretty much drops off after 1. And the same thing for the PACF. There's a significant spike at lag 1 and possibly weaker ones later on. So a candidate for the ARIMA model, given that the data has a difference of D equals 1, and the ASACF and the PACF suggest a short-term AR and MA components are the candidates. So it looks like we might have ARIMA 110, right, with an autoregressive one autoregressive term and one difference term, and one moving average term, right, and both the AR1 and the MA1 term differences. And so we'll get a difference once ARMA 211, right? So the recommendations will start with ARIMA 111 and compare it with ARIMA 110 and 011, and use the Lejeune box test on the residuals and choose the simplest model with the good residual diagnostics. So once again, we'll take a fit of the global economy we'll look for Ireland, right? And we'll have models P1, D1, 0, and P0, D1, Q1, and we'll go ahead and look at their values, right? So if we look at the AIC, we see that we start to search through the models, and we get about 3.12, 3.13, and the BIC about 3.18 and 3.19, between 3.18 and 3.19. And the corrected AIC, once again, is about 313 to about 314. So we can go ahead and look at the residuals. So if we look at the residuals and then look at the ACF and look at the residual plots and see if this is a good value or not. So then we can go ahead and plot it with our model showing the 80% and 95% significance. So let's move on to forecasting, right? So although we calculated the forecast from the ARIMA models in our examples, right, we've not explained how they are obtained. So these point forecasts can be calculated using the following 3 steps. So expand the ARIMA equation so that y of t is on the left-hand side and all the other terms are on the right. And then rewrite the equation replacing t with t plus h. And on the right-hand side of the equation, replace the future observations with their forecast and the future errors with 0 and the past errors with the corresponding residuals to what the errors would be. So beginning with h equals 1, and these steps are repeated with h equals 2 and 3 until all the forecasts have been calculated. So if we look at, we'll illustrate using ARIMA 311. So in this case, the model can be written as 1 minus theta hat, theta 1 hat times b minus theta 2 hat times b squared minus theta 3 hat times b cubed, 1 minus b y of t, and equals 1 plus theta 1 hat b times epsilon of t. So we'll go ahead and expand on both sides and then solve for y of t, right? And we're left with this equation on the bottom. So we have the 2 models, and then we just go ahead and solve for y of t. So next that we have solved for y of t, we'll say y of t plus 1 is equal to y of t times 1 plus theta 1 minus the difference between theta 1 and theta 2, y t minus 1, and then the previous value to that and the previous value to that. So then if we want to find the next value for y, we'll just use the previous value that we have solved for. And we can continue this using our predicted values to predict the next value. So if we look at this multi-step interval for ARIMA 00Q, the models are relatively easy to calculate. So all we have is that y of t is equal to the residual plus the summation of I equals 1 to q, theta I to epsilon t minus I. So the prediction intervals provide for a range within the future value is likely to lie, and they reflect the forecast uncertainty due to the model and the data variability. So example, 95% prediction interval means that the future value will fall within 95%, within the range 95% of the time. When we're constructing these prediction intervals, the interval is equal to the point forecast plus or minus the margin of error. And the margin of error is going to depend on the forecast horizon. So the longer you forecast out for, the more uncertain it is. So we've talked about this many times, right? We said that, for instance, if you're predicting the weather, the further into into the future that you predict the weather, the more uncertain you are of what the actual weather will be. And the model variance and residual standard deviation. So for example, if there's lots of variation in your data, then when you predict it, it's going to be harder to predict. So for example, if your test scores for your last 10 tests were 95, there's a pretty easy guess that your next test will be a 95. Whereas if you've had tests that were in the 40s and tests that were in the 90s, right, it's going to get harder to predict what your next test score will be. So the forecast uncertainty over time, the prediction interval widens as the forecast horizon widens, and it captures the compounding of the uncertainty. So don't forget, we're going to predict the future time, and then use that to predict the next time, and use that to predict the next time. So this is important for planning and risk management, and always report intervals along with the point forecasts. So here we have the point forecast as the blue line, and the light blue shade is the 95% interval. So you're suggesting that this is what your answer is, this blue line. However, your answer could be anywhere within this blue region, and you're 95% certain that the answer will be somewhere in there. Notice as the time increases, your interval gets larger. So here's a R code example, right? We can go ahead and install Fable and Teasable and fit the ARIMA model, right? And we'll go ahead and forecast our value. For seasonal ARIMA models, right? In this case, the seasonal ARIMA model is formed by including an additional seasonal term in the ARIMA model. So we'll have the regular ARIMA model with lowercase pdq, and now the seasonal ARIMA model with an uppercase pdq, and m is the seasonal period, or the number of observations. For example, the number of observations per year. We use a capital uppercase notation for the seasonal part of the model, and a lowercase for the other part. So the seasonal part of the model consists of terms that are similar to non-seasonal components, but they involve backshifts of seasonal periods. So for example, in ARIMA 111, 1114, and a model without a constant, this is for a quarterly data, so m equals 4, and it can be written as in space notation using shown here. So for the ACF and PACF, the seasonal part of the ARIMA, or the autoregressive or moving average model, will be seen in the seasonal lag of the PACF and ACF. So for example, if we look for an ARIMA 000000112, the model will show a spike at lag 12 in the ACF, but no other significant spikes. And exponential decay in the seasonal lags of the PACF, so lags at lags 12, 24, and 36. Similarly, if we have the 0000100 model will show exponential decay in the seasonal lags of the ACF, and a single significant spike at lag 12 of the PACF. And in considering the appropriate seasonal order for the seasonal ARIMA model, restrict attention to the seasonal lags. So the seasonal ARIMA model, also known as S-ARIMA, is an ARIMA with a seasonal component, and it uses the same PDQ and uppercase PDQ for their seasonal part, and the S will be the seasonal period. So, for example, 12 months. And the seasonal differencing, we're going to take the seasonal differences will be performed by taking your value for y at time t minus the value for y at time t minus s, where s is the period of the season, the seasonal period that you're talking about. So, for example, if it's 12 months, then it'll be the value from 12 months ago for the same day. And it may be used along with regular differencing, and sometimes you have to do both. So D equals 1 indicates that one seasonal difference was used. So a full model combines seasonal and non-seasonal components, and the model equations involve non-seasonal autoregressive and moving average terms, and seasonal autoregressive and moving average terms at lag of multiples of S, or your seasonal period. And it captures complex seasonal behavior and data. So the forecast interval widens with the horizon, not surprising, and incorporates both seasonal and non-seasonal uncertainties. And it uses simulation or analytic methods, and the intervals reflect increasing uncertainty, especially at seasonal peaks. So if we look at the seasonal ARIMA model, they're powerful for seasonal time series, and they identify both seasonal and non-seasonal orders, and make sure you check the residuals for white noise behavior, and use the AIC, the corrected AIC in the Lin-Jun box to select the valid models. So, for example, let's look at something like U.S. employment, right? And by the way, if you want to list the values from that database, right? If you wanted to list all the unique industrial titles for U.S. employment, right? We can go ahead and list them here. So we can go ahead and load the packages for FPP3, don't forget, and then Glimpse will help us look at U.S. employment, and we can list all the unique titles and view them. So, for example, let's create something for retail trade. So we're going to look at the U.S. employment data and filter looking for retail trade, and we'll also divide the employed by 1,000. So we end up with number of people in the millions. And we'll go ahead and unplot it, auto plot it with the labels that are shown. So if we go ahead and look at the difference for the employed by 12 months, and also look at a lag of 36, and we'll set this is seasonally differenced. So in this case, we'll show the ACF, and it drops off and falls below at about somewhere around, so near 12, right? And for the PACF, we see a lag well above a spike at 1, and we can go ahead and run this, right? Also, if we look for the seasonal differencing, right, we get a value that looks like this, and we see this dip at January, like between a couple months before January for 2010. If we look for the double differenced, right, we see that that's the plot on on the top, and the ACF has shows a couple of spikes above, so at about 1 and 2 up to about 5 falls below, and then 6 above again, and then we see 1 at 12. And for the PACF, we see 1 at 1 and 3 and at 12. So now we can use this to predict what's going to happen in the future, right? And we'll go ahead and fit the ARIMA model to it using ARMA 111 and 01112, and fit the model in this fashion. And we can go ahead and report how well it did and look at the coefficients for the ARIMA model and show what the AIC and the corrected AIC and the BIC are. So here's another example, right? And we're going to use, this is for U.S. mining and logging employment. And we can see that there's much more uncertainty for the predicted levels, and mainly because there's a lot of uncertainty in what was going on. So there seems to be this seasonal effect of a yearly seasonal effect, but there's also lots of variation in the data, which makes it the 80 and 95% to be much larger than it was last time. So if we look at the ARIMA model versus the ETS model, right? If we look at the ETS model, this is a combination of components, and with modeling with autocorrelations, and the ETS models with multiplicative errors, and also ETS models with additive errors and multiplicative seasonality. And for the ARIMA models, we see all stationary models and many large models, right? And because they're looking at more complex data. And these are fully additive, so they both are fully additive ETS model with the ETS models. So we can look at equivalent relationships between ETS and ARIMA models, right? So for instance, if you remember, here shows the ETS models and what their equivalent would be in the ARIMA models. So in closing, right, what is ARIMA? So ARIMA is auto-regressive integrated moving average, and the model data uses past values and past forecast errors, and it requires stationary data or differencing applied to make it stationary. And the notation we said was PDQ, and for the non-seasonal part, and uppercase PDQ for the seasonal part, and S is the period of the season. And ETS was the exponential smoothing state space model, and it's based on trend, seasonality, and level components. And we said it automatically adapts to changes over time, and the notation was error, trend, and seasonality. So the key differences was ARIMA, the statistical model based on autocorrelations, and it was often better for short-term noisy data, and it requires data processing. So we have to we often have to difference the data. For ETS, we want to decompose the data into its components, and it's often better for clean data with clear structure, and it handles non-stationary data internally. So when do you want to use ARIMA models? When the data has a strong autocorrelation, but no clear trend or seasonality, and the residuals after ETS are not white noise. So if you try ETS and you don't get white noise for the residuals, then try ARIMA. and use ETS when the data shows a clear level trend and or seasonality. And it's simple to interpret, right? You can think about it really easily, that there's a trend and a level and a seasonality. So for example, if we consider an example where we'll use both ARIMA and GUM, and this is world population, and we'll go ahead and look at the two values. So if we look at the ETS model, it's shown here, and this is Guam's population, and this is in millions of people. And if we look at the ARIMA approximation, we get something similar, but it looks like our confidence intervals are thinner for the 80 and 95%. So although they both gave similar output, right? It looks like our confidence levels are sharper for the ARIMA model. So we can go ahead and so if we go ahead and compare these two, right? So this shows the output of selected and estimated by ARIMA, and the ARIMA model does well in capturing all of the dynamics, as the residuals seem to be white noise. So if we look at the residuals and see if they look like white noise, then it should be good. And here we show a graph of the residuals diagnostics for the ARIMA model. And if you notice that ACF is well below the level, and we see that it looks pretty much like white noise. So if we look at the ETS model, and in this case, we're looking for cement, right? And we could go ahead and see what the output is. So in this case, we see what the values are for the AIC, and the corrected AIC was about 1104 and about 1106, and a BIC of about 1121. So if we fit the ARIMA models and fit the ETS models, we can compare them by looking at the accuracy and the forecast of both of these models. So here we see the ARIMA model, and this is cement production in Australia, and we can look at our confidence levels.